Okay, so that's a major philosophical break from classical mechanics, difference from quantum mechanics. So what we have here is that in the case of vertical transition, the initial momentum before the electron, absorption of the photon, and the final momentum after absorption of the photon must be the same. And in order to have this excitation to take place. And in order to, as you may remember, this momentum that you got in the solid is ambiguous. It's ambiguous in the sense that if I change my momentum by a residual lattice vector, indigo or residual lattice vector, I would not know that I have actually changed my momentum. The reason is periodicity, right? Because you have three-dimensional periodicity. So in order to have this three-dimensional periodicity, it got to be the property of your point must be invariant under translation, and this translation invariant lead to this residual lattice. And so if you translate yourself from one lattice point to another, you will not know any difference. Okay? Because of this invariant effect, you would have ambiguity, because ambiguity in the sense that if you add anything with the residual lattice spacing, you would not know that you have moved. Okay? So therefore, what you have to do is to say that, well, here Ki initial is equal to Kf, like this. That's fine, but because of spatial invariant translational symmetry, sometimes called, you could have Ki, you could have Kf equal to Ki plus a G, which is a residual lattice, and that would also be allowed because you would not know any difference, and you can set this to 0, or you can set it to multiple of G, and it will be fine. You will not know any difference. Okay, so so it is important in this case. This is a three-dimensional, right? This where I'm writing my vector, the momentum of my conservation momentum of my electron before and after photon absorption, like that. But in the case of surface, there's something different, something unique occur, because in the case of surface, you don't have three-dimensional symmetry anymore, right? You only have two-dimensional symmetry, and that breaks the symmetry of the perpendicular direction. So the perpendicular direction, you have no control of this. You do not need to obey any sort of conservation law, but in the parallel direction, you have to obey conservation law because you have symmetry of the surface controlling. Okay, so just let me talk us briefly about this. So I have written a little bit quick notes on this. I write this energy conservation and momentum conservation of the photoelectron. Right, this is initial state and final state. Okay, so this is. Of course, the final state should, after the absorption of the photon, should be equal to the EI plus the photon energy. And of course, in the case of momentum conservation, this is what happens. It's after photon absorption, Kf, before photon absorption, plus a G. Okay, so the picture I have is that I have this photon, with light coming in, photon absorption occur at this point. There's two directions of this vector. One is this perpendicular direction, and the other is in plane, pointing out you along this plane, inside the plane. So, and this electron must move from this point to the outside. Okay, so what I try to do is to classify this as inside the surface, below the surface, and outside, to see what happened as the photoelectron moves to the surface itself. So it's quite simple in some way, because if you look at what is inside, so the final state inside, right? If you look at just the momentum conservation using this momentum conservation equation, if you're looking at inside is the bulk, right? So the absorption inside the bulk. So that's okay. That follows the G vector of the bulk. So residual lattice of the bulk itself. So I write G sub B. So this is conservation law due to invariant of the 3 dimensions. And then, of course, you look at kinetic energy of your electron is equal to P squared divided by 2m, right? That's essentially kinetic energy. And in quantum mechanics, you can write P as h pi times k. K is the wave vector, which we've been talking about. And h pi, of course, is the same as Planck constant divided by 2 pi. So it's just a constant. So P is like K is like P, except it's K is proportional to P. Yes.
How come the reciprocal lattice vector is equated to the momentum here?
Say it again. How come the
reciprocal lattice vector G
Yeah.
of B?
Yeah.
How is that equated to the momentum? Because the units are different, right?
Yes. You have to you can write it in a way that the unit is the same. The physics is the same because it's just a unit translation. So you speak a lattice, you can rewrite it. Usually it should be 1 over space, right? 1 over the spatial dimension. And in this case, the wave vector is also 1 over the residual space dimension. So think of it that way. In dimensionally, they're okay. There may be some constant missing between the two. Okay.
So that means it undergoes a translation of equivalent to 1 unit or something?
So you can think of it, if you want to get the unit the same, you just consider adding multiply a constant to GB, then you should get them the same. It's a way how you write it in the same kind of unit. But dimensionally they are the same because they are reciprocal space, 1 over residual space. And so what you got is that you have the kinetic energy term is proportional P squared divided by 2m, and you expand this out, right? Basically Px squared, Py squared, Pz squared divided by 2m. And you group these 2 terms together, and you call it P parallel squared. And this is P perpendicular squared, like this, okay? So you just sort of separate them out into the parallel direction, meaning that on the surface, right, parallel to the surface, and then perpendicular meaning, so it's like this. Parallel means that it's along the surface, perpendicular is perpendicular to the surface of this plane. This plane is, of course, coming out at you, so you're looking from the side view of this material. So you can rewrite this into these 2 terms. It's just a way you divide up your energy. So it's just P squared parallel plus divided by 2m plus P squared perpendicular divided by 2m. And so that's it. So you sort of divide it out into 2 terms. And then your kinetic energy, according to Einstein equation, should be equal to your final state energy, right, minus the work function. Okay. And here, at the surface, what happened, what I'm focusing in is that what happened at the parallel direction, if I look at the surface inside and outside, right, look at the surface inside and outside. So we have Kf parallel is equal to final state, right? The electron has moved to the surface. Must follow conservation law, because if you're looking at the momentum at this point on the surface, is on the outside, right, which is escaping, must equal to Kf at this point on the inside plus the residual spacing of the surface, residual lattice of the surface itself. Because here I have a invariant along the surface in the parallel direction only. I don't have invariant, I don't have conservation in the perpendicular direction because I have termination of my bulk on the surface. So at the surface, this plane is unique because it only have 2-dimensional symmetry, whereas below this surface, I have 3-dimensional symmetry. So I only need to consider parallel component to be conserved with the residual lattice of the surface G sub S here. Whereas below, I have to consider three-dimensional symmetry with the conservation of G sub B here, like this. Okay. And of course, if you look at the inside, right, you look at this term, you can rewrite it like this, just algebra, and the inside of the parallel direction from this equation star, which is equation star here. So now I'm connecting inside and outside of my final state of the electron. Now I'm connecting my final state inside, okay, to my initial state inside, before the absorption of photon. So before the absorption of